Hi everyone. In this video we are going to discuss about how to determine the equation of the bisectors of the angles between two straight lines. Here in the diagram we have two straight lines, straight line A and straight line B. A's equation is A sub 1 times x plus B sub 1 times y plus C sub 1 equals 0, and straight line B's equation is A sub 2 times x plus B sub 2 times y plus C sub 2 equals 0. And these two straight lines are intersecting lines, but they are not perpendicular, so they create an acute angle and an obtuse angle between them. Like in the diagram, I have the acute angle denoted as alpha and the obtuse angle denoted as beta. So alpha is the acute angle, beta is the obtuse angle, but they both are angles between these two straight lines. Now if we think about angle bisectors, then obviously there will be two bisectors because there are two different angles between the straight lines. So there should be a bisector for the alpha angle and also there should be a bisector for the beta angle. And let's assume that the bisectors kind of look like this. The bisector for the alpha angle looks like the yellow dotted line that I have on the diagram, and then the bisector of the beta angle is the dotted green line on the diagram. We know the equations of the original straight lines. Somehow we have to figure out what would be the equation of these two bisectors. Now I'm going to give a name to each of these bisectors. Let's suppose this bisector is B sub 1, bisector sub 1, and the other bisector, which is in yellow color, I am writing it as B sub 2. So how are we going to find out the equation of these two bisectors? Well, in one of the previous videos, I have explained angle bisector as a locus of a point. I have shared the link in the description. Feel free to watch that video. There I have explained how an angle bisector is nothing but the locus of a point that maintains an equal distance from the two straight lines. So suppose we have a point like this. Let's suppose we have a point P whose coordinates are h, k, and this point is of course on the angle bisector. In fact, if you think about P as a moving point, and if P moves in such a way that it always maintains an equal distance from two straight lines, two intersecting straight lines, then the locus of this point will be nothing but the angle bisector between those two original straight lines. Now how can we prove it? Well, let's try to drop a perpendicular from P onto the straight line A and straight line B. So I'm going to drop two separate perpendiculars from the point P. Let's suppose the perpendicular from P onto the original straight line A landed on the point Q, and the perpendicular from P onto the original straight line B landed on point R. And let's give a name to the intersection of the original two straight lines. Let's say that is point O. So I am writing in red color. Let's assume that that is point O. Now since I have drawn perpendicular from point P onto the original straight lines, I should denote the right angle right there. So now I am denoting the right angle, angle PQO and angle PRO. Each of them is a right angle because I dropped a perpendicular from P, right? So now if you look at the two triangles, the OPQ and OPR, these two triangles, they are two right triangles and they have a common hypotenuse which is OP, and because P is such a moving point that it maintains equal distance from two intersecting straight lines, then let's assume that the distances PQ and PR, they are equal. So now we have two right triangles where the hypotenuse is common and also one other corresponding side is of equal length. Then obviously the two right triangles are congruent triangles. So we can say that the triangle OPQ is congruent to the triangle OPR, and then the corresponding angles QOP and ROP, they will be equal. Because the two triangles are congruent triangles, so their corresponding angles QOP and ROP, those two angles will be equal, and actually they will be then half of beta because the obtuse angle between the two original straight lines was beta, and now we could prove that beta has been divided into two equal parts. That means the locus of this point is actually bisecting the angle. So the locus is actually the angle bisector, and in that case we know that it maintains equal distance from the two straight lines. So I am indicating that the line segments PQ and PR, they are actually of equal size. So if a moving point P moves in such a way that it maintains equal distance from two intersecting lines, then its locus will be like an angle bisector. And if you want to say it the other way, that if we have an angle bisector between two intersecting straight lines, then obviously it is nothing but the locus of a moving point which is moving in such a way that it is maintaining equal distance from the two intersecting lines. Now let's try to find out what would be the equation of this angle bisector. Using the formula for distance of a straight line from a point, can we say that then PQ would be equal to modulus of a sub 1 times h plus b sub 1 times k plus c sub 1 over square root of a sub 1 squared plus b sub 1 squared. I have already created a separate video on this particular topic, distance of a straight line from a point. I have shared the link in the description. Feel free to watch that video. I am just simply using the formula. I am plugging in the coordinates of the point P into the expression of the first straight line, which is straight line A, and using h and k in the expression for the straight line A, we get the distance PQ as modulus of a sub 1 times h plus b sub 1 times k plus c sub 1 over square root of a sub 1 squared plus b sub 1 squared. Similarly, what would be the distance of PR? Well, PR will be equal to modulus of a sub 2 times h plus b sub 2 times k plus c sub 2 over square root of a sub 2 squared plus b sub 2 squared. And then if you see our important property right here, that PQ will be equal to PR, I have kind of highlighted that with a light green color box. So PQ equals PR, that is our most important property right here of this angle bisector. And if we use that equation, then we can say that these two lengths would be equal. So let me write it down. And from here, if we remove the modulus sign, we can write it as something like this. Now why plus or minus? Well, if we have two modulus expressions in an equation, then when we remove the modulus sign, then we have to denote it like this, because from the discussion of modulus function, we know that if we have modulus of x is equal to modulus of y, then we can say that x must be equal to plus or minus y. That is one of the important properties of modulus function. I have created a separate video on this topic. I have shared the link in the description. Feel free to watch that video. So using that property, we have been able to remove the modulus sign in our equation here, and here we get two equations actually, one with the positive sign on the right hand side and another one with the negative sign on the right hand side. So essentially this gives us two equations. Now why two equations? Well, because we have two bisectors. We have the bisector b sub 1 and we have the bisector b sub 2. So actually we have been able to find out the equations of both of the bisectors. So one of the equations would be with the plus sign and another one would be with the minus sign. But again, we wouldn't know which one is the equation for bisector b sub 1 and which one is the equation for bisector b sub 2. There are other techniques to find that out and we'll be discussing that in the subsequent videos. But for now, just remember that these two equations are the equations of the bisector b sub 1 and b sub 2. One of them has the positive sign on the right hand side and the other one has the negative sign on the right hand side. Next, we are going to look at this concept from an analytical perspective. In a previous video, I have already discussed about position of a point with respect to a straight line and how a straight line divides a plane into two distinct regions. One side of the straight line would be a positive region and the other side would be a negative region. I have shared the link in the description. Feel free to watch that video. Now here, let's assume that we have a straight line A, whose equation is given by a sub 1 times x plus b sub 1 times y plus c sub 1 is equal to 0. And this straight line is dividing the plane on which I have drawn this straight line. Let's suppose that the right hand side of this straight line is the positive region. So let me highlight that. And let's assume that the left hand side of this straight line, meaning the plane on the left hand side, is the negative region for this straight line. And I have denoted that with a bunch of negative signs on the left hand side. Now let's draw another intersecting straight line. Here I have the second straight line in white color. I have named it as straight line B. And let's suppose its equation is a sub 2 times x plus b sub 2 times y plus c sub 2 equal to 0. For this straight line also, let's assume that it's dividing the plane in two distinct regions such that the right hand side of the plane is the positive region for it, and I'm going to denote that with a bunch of yellow plus signs. And let's assume its left hand side is the negative region. I'm going to denote that with a bunch of red minus signs. So in this picture, as you can clearly see that there are 4 unique regions, and in each pair of those regions, which are kind of on the opposite side of the angle, right? So each pair of the opposite angle regions, they have same sign for both of the straight lines. For example, if you look at the right hand side, which is the obtuse angle region, on the right hand side it's positive for both straight lines. Similarly, the opposite side, which is on the left hand side for the obtuse angle, that is negative for both straight lines. And then if you look at the acute angle up there we have a mix of positive and negative. That means for one straight line, the coordinates of any point in the region would make the expression negative, and the other straight line, it will make it positive. Similarly, down below where you see we have a mix of positive and negative again for the opposite acute angle there again coordinates of any point from that region would make the expression of one straight line as positive and the expression of the other straight line as negative. Now let's assume that we have the point P right here. Let's assume that the P point is right here. Now in that case, if we use the coordinates of P in the expression of the straight line edge equation, then that will give us a positive value. I mean, if we use this in the expression, left hand side expression of the straight line edge equation, and what is the expression? Well, the left hand side expression of straight line edge equation is like this: a sub 1 times x plus b sub 1 times y plus c sub 1. And if we plug in the coordinates of P in place of x and y, then this is going to become a sub 1 times h plus b sub 1 times k plus c sub 1. And because it is on the positive region of the straight line A, so this value will be positive. Can we also say that this value will also be positive? This denominator is a positive number, so I simply divided it by this denominator, so this quantity will also be greater than 0. That means the perpendicular distance of P from the straight line A is actually a positive quantity. So this distance is a positive quantity. And similarly, if we look at the equation of the straight line B, then its expression is like this: a sub 2 times x plus b sub 2 times y plus c sub 2. And if we plug in the coordinates of P in place of x and y, then we are going to get a sub 2 times h plus b sub 2 times k plus c sub 2, and this is also going to be positive because we are in the positive region of straight line B. I mean, P is in the positive region of straight line B. So then if we simply divide this by a positive number, which is square root of a sub 2 squared plus b sub 2 squared, that is also going to be a positive quantity. So in this case, you see this is nothing but the distance of P from the straight line B, that also turns out to be a positive quantity. So in this particular example, if the positive and negative regions happen to be the way we have assumed, then both the distances are coming out to be positive. Then we can say, well, then PQ equals PR, you know, our original property up there. So I'm going back to the original property, which is way up there. You can see right here that the original property right here, I'm kind of highlighting here, that this property PQ equals PR, the two distances being equal. So if the straight lines are like this, then obviously these two distances are both positive. So we can say, well, then the bisector on which the point P exists, that bisector's equation will be the equation with the positive sign and not the negative sign. So if we take the positive sign, that will give us the equation of the bisector that bisects the obtuse angle between these two straight lines for this particular situation, the way we have assumed, right? And now if you think about it, if we have P in another region, say for example, if we had P somewhere here, let's say now I am assuming that our P was somewhere here, let's say right here. Suppose this was our point P, and let's again assume its coordinates are h, k. So if P was right here, which is actually on the bisector of the acute angle, then you can see that the expression of straight line A will give us a positive value because we are still on the positive region, positive side of the straight line A. So here we can say that this is going to be positive, a sub 1 times h plus b sub 1 times k plus c sub 1. This is going to be positive, and again if we divide that by another positive quantity, which is square root of a sub 1 squared plus b sub 1 squared, so this quantity is going to be positive. But if you think about the straight line B and its expression, so if we use B's expression, which is a sub 2 times h, I am using p's coordinates of course, then plus b sub 2 times k plus c sub 2, this will be a negative quantity. Why? Because now P, the yellow colored P, it is actually on the negative region of the straight line B. So in this case, this quantity will be negative, and if we divide that by another positive quantity, which is like this, a sub 2 squared plus b sub 2 squared, that quantity will be negative. So now here you see we are getting one distance as a positive value and another distance as a negative value. But in our original equation PQ equals PR, those are nothing but positive distances. We are simply talking about distance without any sign. The PQ and PR, here we have no sign. Both are positive. So let me write it down right here. I am saying both positive. PQ and PR, they both are positive. Now if both have to be positive, then what happens in this example? Well, in this example we are getting one quantity as positive and another quantity as negative when P is the yellow P, which is like in the acute angle region. So then in that case we have to use a negative sign when we equate them. So here if I want to equate them, assuming left hand side is PQ and right hand side is PR, then if I want to equate them, we have to use the negative sign. Think about it, because PQ and PR, they both have to be positive. So left hand side PQ, that is positive, right hand side PR, assuming it is PR, that is coming out to be negative. So I am forcefully multiplying by a negative 1, or I am using a negative sign in front of it on the right hand side to make it a positive quantity. So by adding this negative sign on the right hand side, I have been able to make it a positive quantity. I mean the right side quantity is a positive quantity now because I am using a negative sign extra. But the left hand side came out to be positive anyways, so we are fine with the left hand side, and on the right hand side we have a negative sign. But when P was in the obtuse angle region, like in the pink color, there if we wanted to equate both of them, they both turned out to be positive. Here you see it was greater than 0, here also it was greater than 0. Both the distances turned out to be positive. So if we equate them, then just using the positive sign would be good enough for that bisector. So this is how in one region both distances will be of the same sign, and in another region the distances would be of opposite sign. So for one region, in this particular example, the way we have assumed, when P is in the obtuse angle region, both distances would be of the same sign. I mean they both either will be positive or they will be negative. If P happen to be on the left hand side obtuse angle region, then both quantities will come out to be negative. So in any case, we are going to get the distances with the same sign, and when both the distances are with the same sign, either both of them are positive or both of them are negative, then simply using the positive sign when we equate them is good enough. And in the other regions, like in this example where we have the acute angle regions, there you see the distances are coming out to be opposite signs. One would be positive, another one would be negative. So in that case, we have to use one extra negative sign. So that is why we have the equations of the bisectors kind of like this. One will have the positive sign and the other one will have the negative sign. So if I may summarize it like this, so we can say that a sub 1 times h plus b sub 1 times k plus c sub 1 over square root of a sub 1 squared plus b sub 1 squared. We can say this is equal to, let's take a positive sign, and then on the other side it would be a sub 2 times h plus b sub 2 times k plus c sub 2 over square root of a sub 2 squared plus b sub 2 squared. So that is one equation, and the other equation, meaning the equation of the other bisector, would be like this. It will be with the negative sign of course, so we can write it as a sub 1 times h plus b sub 1 times k plus c sub 1 over square root of a sub 1 squared plus b sub 1 squared, and then we can write it as negative sign of a similar looking quantity like this. That would be a sub 2 times h plus b sub 2 times k plus c sub 2 over square root of a sub 2 squared plus b sub 2 squared. So those are our two desired equations. One of them will be the bisector of the obtuse angle and the other one will be the bisector of the acute angle. Now which one is the obtuse angle bisector and which one is the acute angle bisector, we are going to discuss that in another video which will be coming up soon, and there I will show you how to determine which equation is for the acute angle bisector and which equation is for the obtuse angle bisector. But for now just remember that one of these equations would be the obtuse angle bisector and the other one will be the acute angle bisector. Now if we generalize the equation here, as you can see I still have h and k in these equations, and if I simply replace that with an x and y, then the equation is going to kind of look like this. Here I am going to erase and change them to x and y, so I am going to replace h and k by x and y, so they are going to look like this. I am simply making it a general equation here, so in place of h I am using x and in place of k I am using y. If we simply assume that the coordinates of the point P are x, y, then the equation is going to look like this. And similarly on the second equation also, let me replace the h and k by x and y. So those are our two equations for the angle bisectors. Next I am going to take an example to see how to figure out the equations of the angle bisectors. Suppose we have been given the equations of two straight lines which are like this, and we have to find out what would be the equations of the angle bisectors, and these two straight lines are obviously non-perpendicular because if you look at their slopes and if you do the product of their slopes it will not be -1, so they are not perpendicular, and also they are not parallel because their slopes are different. So now what is the general equation of the angle bisectors? Well, the equations are kind of like this. So the numerator portion is essentially the expression of each of those equations there, and we just have to find out the denominator here. So on the left hand side we can write it like this. We can use the left hand side expression of the first equation for one of the bisectors. So let's say this is bisector b sub 1, right? So for b sub 1 we are going to take the positive sign. So let's assume that we are talking about the bisector b sub 1. And for this bisector we are going to take the positive sign, so the left hand side will be the left hand side expression of the first equation, which is x minus y plus 2 over square root of what is a sub 1. Well, a sub 1 is actually positive 1, so that is positive 1 squared, plus what is b sub 1. Well, b sub 1 is actually a negative 1, so negative 1 squared, that is equal to, I am going to use a positive sign for the first bisector. Then on the right hand side numerator we can use the left hand expression of the second equation, so that would be 2 times x plus y minus 6 over square root of what is a sub 2. Well, a sub 2 is actually positive 2, so positive 2 squared, plus what is b sub 2. Well, b sub 2 is actually 1, so positive 1 squared, so it will be like this. And from here this is x minus y plus 2 over square root of 2, that would be square root of 1 plus 1, so it will be square root of 2 is equal to positive, so this is 2 times x plus y minus 6 over square root of 4 plus 1 5, so that would be square root of 5. And from here can we write it like this? It would be square root of 5 times, I am simply doing a cross multiplication, is equal to square root of 2 times, and from here if we simplify this we have square root of 5 times x minus square root of 5 times y plus 2 times square root of 5 is equal to 2 times square root of 2 times x plus square root of 2 times y minus 6 times square root of 2. And from here if we bring all the terms to the left hand side, then this would be square root of 5 minus 2 times square root of 2 whole times x, so we will have so many x, and then minus we have a square root of 5 here and then another negative square root of 2, so that would be positive square root of 2 like this times y, and then plus 2 times square root of 5 and plus 6 times square root of 2, that is our constant term, and that is equal to 0. So that is one of the equations of the bisectors. And then we are going to calculate the equation of the other bisector. So let's quickly do that. For equation of the other bisector, let me say this is suppose b sub 2, that's the second bisector we are talking about. Then again it will be pretty much similar, we just have to take a minus sign on the right hand side. So that would be x minus y plus 2 over, I am directly writing it as square root of 2 because you already know it is square root of 2, is equal to, this time I am taking a minus sign. Carefully make a note of that. I am taking a minus sign, then it will be 2 times x plus y minus 6 over this will be square root of 5, and from here if we do the cross multiplication, so this would be square root of 5 times x minus y plus 2, and then on the right hand side it would be negative square root of 2 times x plus y minus 6. And if we bring everything to the left hand side, then we are going to get something like this. It would be square root of 5 times x minus square root of 5 times y plus 2 times square root of 5, and then plus 2 times square root of 2 times x, and then plus square root of 2 times y, and then minus 6 times square root of 2. All of that is equal to 0. And now if we combine the x terms, then we have a square root of 5, which is right here, and then we have a 2 times square root of 2, and that's a positive one, so 2 times square root of 2, so all of that times x. And then for the y terms, we have a positive square root of 2 and a negative square root of 5, so we can write it as positive square root of 2 and negative square root of 5 times y. And then for the constant terms, we have 2 square root of 5 and negative 6 square root of 2, 2 square root of 5 and negative 6 square root of 2. All of that equals 0, and that is the equation of our second bisector. I hope everything made sense. Thank you for watching. See you in the next video.